Hi, this is Sharanya, Assistant Professor, EC Department. Today we are going to discuss about pulse modulation. Modulation is required for a signal to be transmitted in a proper way. So for that, we require a message signal and a carrier signal which has to be modulated with the help of modulators. We have many types of modulation like your amplitude modulation where you change the amplitude, your frequency modulation and phase modulation. So today we are going to see about pulse modulation. So this pulse modulation is where the carrier signal will be considered in the terms of pulse. So this is what is pulse modulation. So the definition goes like this. In pulse modulation, some parameter such as amplitude, width and position of a carrier pulse strain is varied in accordance with the instantaneous amplitude of the message signal. So with the a trace of the message signal and the carrier as a pulse signal, we will modulate the signal, we call it to be as a pulse modulation. So here the carrier will be a train of discrete pulses. So the classification of PM, that is the pulse modulation, is divided into two types. One will be your analog type and another one will be your digital type. So analog, there comes the PAM and PTM. So PAM is pulse amplitude modulation and PTM is we have two things. One we call it to be as a pulse width and pulse position. So this is comes under continuous. When the signal input signal is considered as a continuous signal, you call it to be as an analog pulse modulation. When I'm considering my input to be as digital form, you call it to be as a digital pulse modulation, where you'll be considering the input as samples of zeros and ones. So in that subdivision we are having the PCM and delta modulation, and above that we have the adaptive delta modulation and differentiated pulse code modulation. So these are the what is say the types which comes under the digital. Okay, so today thing we are going to discuss about what is PAM, PWM and PPM. So these all three things comes under analog processing. So first is what is analog PM. So as I told you, when I'm taking a continuous signal with a discrete time of train of pulses to modulate, you call it to be as an analog pulses. So you can see the changes in the pulse, you call amplitude changes, you call it to be as pulse amplitude modulation, and the width of the pulse changes, you call it to be as the pulse width modulation, and the position of the pulse changes, you call it to be as a pulse position modulation. So analog modulation, the amplitude, width or position of the pulse can vary over a continuous range in accordance with the message amplitude at the sampling instant. So this is the definition of the amplitude PM. And the digital, as I've told, it is transmitting the samples of discrete values, and these are the two types. So first we'll see what is PAM, pulse amplitude modulation. So definition is which deals about the amplitude changing where the width will be the constant. So the amplitude of the pulse carrier is varied in position with the amplitude of the continuous modulating signal. So modulating signal is nothing but your message signal. So message signal in accordance with the carrier signal, which is of pulse train, you'll be using in order to modulate. So only the amplitude alone is varied, where the width and position of the pulses is constant, you call it to be as a pulse amplitude modulation. So the width and position will be constant. So here you can classify into two types. One will be your natural PAM, and another one is the flat tops PAM. So first we'll consider, see, this is a train of pulses, and you can have this is my sine wave, which is a continuous signal. So these two are bombarded and I'm getting the output to be like this. Okay, so you can see the trace is coming like this, where I'm having the top of my signal to be chopped. Okay, so this is cut, this you call it to be as a natural PAM. When it is of flat, okay, when the output waveform it is of flat pulses, you call it to be as a flat top. will be discussing further. So first we'll consider about natural PAM. So you can see the as the trace of the continuous input signal goes, you can see that pulses gets cut chopped like this. So this you call it to be as a natural PAM. Okay, so this can be obtained by when I'm using my input signal to a low pass filter, then a pulse generator. This is what the train of pulses. When I'm both multiplexing, that is I'm multiplying the operation, I'll be getting the this type of output. Okay, so this is the output I'll be getting. Okay, so the amplitude of each pulses is directly proportional to the modulating signal amplitude at the time of pulse occurrence, and then follows the amplitude of the modulating. So it continuously follows the input signal, and with the help of this pulses it forms the wave. So this you call it to be as a natural PAM. So flat top, as I told, the it won't get chopped here. You can see the full pulse is coming here, and here you can see above the sine wave you can see the pulse, and this you call it to be as a flat top PAM. So flat top PAM is mostly recommended because it will be easy for us to reconstruct my original signal from the flat top, whereas more noise, as we are chopping the signals in the natural, it is very difficult to reconstruct the signal, whereas in flat top we can easily reconstruct a signal. That is, after the detection process we'll be able to get the signal in a proper output. So most of the thing will be going with the flat top PAM. So flat top PAM is the best for transmission because we can easily remove the noise, and we can also easily recognize the noise. So this is the main advantage of flat top. So this is the generation part. As I told, I'll be having the message signal low pass, I'll be sending the signal, and the C of t is the pulse train which I'm getting the carrier signal. Both is mixed, and this is the part I'll be getting my PAM signal. Okay, so here this will be the what do you say, the detection part. So this signal has to be sent to the reconstruction filter, which is nothing but the low pass filter, then to the equalizer. So whatever gets attenuated, or which is to equalize the changes in the low pass, we'll be using a equalizer circuit here, and you will be getting the original output. So how this is the from this signal I have to generate my flat tops. So how it is possible? So this is a circuit which helped me to generate the processing. You can see the flat tops here. Okay, so here I'm having two FET. Okay, say one will be this acting, both acting as a switch, like, so this will be the sampling switch, and this will be the discharge switch. So this is the generation of flat top PAM. So here I'm giving my input signal, and here you can see two FET here and a capacitor, and here will be my output. So how the processing actually occurs is, first you consider this diagram. Okay, so this is my, I'm considering my input signal. Okay, so which I'll be giving to here, I'll be giving here as my input signal, and here in this FET and this position, these two position, first this position I'll be giving the discrete samples. Okay, so this will be my discrete sample. So what will happen, this is my train of pulses, and this is my input signal. So these two gets multiplied with the multiplexer, and I'll be getting like this the output. So I'll be having the train of trace of the input signal and the pulses at each instant. So you can see x of t and dou of t. The s of t is equal to x of t into dou of t. Okay, so this is the output which is generated by the sampling switch. So here I'll be having the output. Now at this stage I'll be giving the pulse train here. Okay, so this will be acting as a discharge switch. So what will happen, these two, this input and this input will be combined, and I'll be getting like this. So this sample, say ts, is made to hold till the pulse gets completed. So here, from starting from here to here, the ts will be maintained. Okay, so one pulse, if it is starting here and it is, if it is ending here, this is the whole ts. Okay, so this is how it gets to be sample and hold. So I'm what initially I'm sampling my signal and I'm holding my signal to the time period of ts. Okay, so like this 2 ts it gets holded up, and this you call it to be as a sample and hold condition. So flat top mainly deals with that of the sample and hold condition. So first the sample and hold circuit is produced, and we having the FET and we having the input signal. So the dou of t is given to the charging switch, and you have to multiply, and you'll be getting the s of t, and h of t is given to the discharge switch, and these two will be combined and you'll be getting g of t, where tau will be my period. Okay, so this width of this pulse will be tau. So tau, so each pulse will be having tau period in order to take the pulse width. Okay, so this is how the thing is generated. Okay, first initially a message signal, low pass with a pulse train, I'll be getting a normal natural signal, and with the help of the flat top I'll be able to generate a flat top PAM. Okay, so this is the main thing. So here will be occurring an aperture effect. Okay, so this aperture effect, as per the definition, you can say during flat top sampling, in order to convert varying amplitude of pulses to flat top pulses, we use a zinc function. So because of this, there would be a decrease in the amplitude. Okay, so in the reconstruction, while sampling and reconstruction we have discussed, the reconstruction process will be having a net of frequencies which will be overlapped. You'll be having net, and when you trace it, you call it to be as a zinc function. Okay, so this zinc function, after the detection part, there will be decreasing in the amplitude. So this effect and the reconstruction low pass filter, everything will be equalized with the help of this equalizer, and it is sent to the output as a proper sine wave will be getting as m of t. Okay, so this is the reconstruction part. And the detector I have discussed with will be having low pass filter, and will be having the equalizer which compensate both the aperture effect and as well as the attenuations in the low pass filter. Okay, so this is PAM, and the bandwidth, if I'm considering, it is, I have told it is tau. So tau plus tau, it is of 2 tau for the positive and negative half cycle, if I'm considering. So the bandwidth will be 1 by 2 tau. Okay, so the advantage here, it's very simple, and the generation part and detection part, if you see, the thing is very simple to construct, and easily you can get the output. Not much difficulty, you can it's there. But disadvantage, you can see, it is of bandwidth is too large and you have more noise. Why more noise means my amplitude gets changes. Okay, so as amplitude changes, obviously there will be noise, and the power is not constant. And so this is also the same, as the amplitude varies, the power has to be varied according to the height of the amplitude. So at the transmission side, the power gets varied based upon the pulses amplitude. So the power is not constant. So this is the disadvantage which we are facing. So next we'll go upon to pulse width modulation and pulse position modulation. So